So questions from the homework from last day, number 9. I'm going to dulp, Jaron. There's my ramp. Where it says this is 20 meters. And it says this is 20 degrees. And here's the mass. What are the forces acting on this mass? Get the obvious one. And it says we're pulling it up at a constant speed, so here's our applied force. And Jaron, what I really think we're saying is that our applied force is exactly the same size as mg parallel, because gravity's pulling it down the ramp, someone's pulling it up the ramp at a constant speed. So when A says what force is required to pull the mass up, I think it's really mg 2 lines is sine. It's that. It's going to be 10 times 9.8 times the sine of 20. 33.5. Is that okay so far, kiddo? And that is force newtons. How long is the ramp? Okay, now I'm going to do some basic trig. This length here is x. Jaron, here's my angle. Opposite, yes? Yeah. Hypotenuse. Which trig function? I can find the length of the ramp by going sine of 20 equals opposite over hypotenuse. In fact, the length of the ramp is going to be 20 divided by sine 20. Unfortunate, they're both 20s, but that's okay. One's an angle, one's a length. Whatever the heck that is. 58.5, apparently. What's C asking me to find? How much work was done? Oh, Jaron, work was what times what? So, which force? Well, it's up the ramp, so it must be the applied force, which was mg parallel, the same magnitude. Which distance? It's going to be mg sine 20, there's the force up the ramp, times, what was the length of the ramp? 20 over sine 20. It's going to be that. Oh! Does anybody notice something a little neat, that kind of cool that happens here? Turns out, Jaron, my friend, the sine 20s cancel, and that leads us to part D. Part D says write a work energy equation. Another way we could have calculated the work is to say mgh, because the force that you're doing work against, Tyler, is gravity, and the height that you're lifting it is 20. What I'm trying to reinforce here is energy is a scalar. It doesn't care about the path that you took. Do you notice you actually do get mgh from that previous equation, going winner minus doing the big long force stuff? We could have just gone, for Pete's sakes, gravity, mgh, which is why E is also the same answer as C. Kind of cool. Any others? Oh, yes. Gabby, kinetic energy is equal to what? What's the equation?
1/2 mv².
Louder, sorry?
1/2 mv².
A half mv what?
Squared.
Half mv what?
Squared.
I think it's going to be a parabola.
42.
Yep. Okay. I'm not quite good. By the way, I did that one purely because in Math 11, most of you looked at the parabola and wow, another nice use of it. But I probably won't ask you something like that. In fact, I'm pretty sure I don't ask you something like that on your test.
So is it
Pardon me? I don't know. We just answered that little miss paying attention and forgetting her binder person. You with me now? Yes, Steve. The second one. By the way, I know the third one's definitely wrong because the kinetic energy has to be increasing and the third one has a constant kinetic energy. No, it's speeding up. I've dropped things. They speed up and they gain kinetic energy. Right? So it's either the first or the second or the third. It's a half mv squared. It's a lovely parabola. Lesson 2. What is the law of conservation of energy? Well, in English, it says this. The total energy of a closed system is neither increased nor decreased in any process. Energy cannot be created or destroyed. It can be transformed from one form to another, but the total remains constant. Now, I said a closed system. What I mean by that is there's no outside external energy sources. When you plug something in, you're drawing energy from the powered hydroelectric system somewhere. Well, that's not a conservation of energy on your iPod device. It's pulling energy. It's not a closed system. But if we close off all external sources, the amount of energy before equals the amount of energy after. The way we traditionally write it is like this. The two main types of energy we're looking at this unit are kinetic and potential. So the amount of kinetic originally plus the amount of potential originally equals the amount of kinetic energy at the end plus the amount of potential energy at the end. Or if we include friction, we would say this. The amount of kinetic energy that you begin with plus the amount of potential energy that you begin with equals the amount of kinetic energy that you end with plus the amount of potential energy that you end with. And whatever's left over goes into heat. Technically, heat and sound and other dissipative energies, but we're just going to classify it all as heat. Where does this come from? Really what we're saying is this. Work is equal to what times what? That was one definition, but then we also said it was the area underneath the force versus distance graph. But we also said, we gave you the work energy theorem. We said that work was equal to, do you remember? And if I have a closed energy system, what we're really saying is the net work is zero. What's changing anything? Oh, not plus, Mr. Duick, minus. There we go. Can you see by writing that, Brian, if I plus both the initials over to the other side, I get this line right here because it's a zero there. I've jumped straight to this. You're going to notice in your answers that the author who wrote my answer keys usually starts up here with work. You know what? This is one of the times when I say, even though this formula is not on your formula sheet, well worth memorizing. And you will because you'll use it so often. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Are they talking about friction? They are, plus heat. No friction, no heat. I wrote down here, Mr. Duick has a good demo for this. Yeah, I got a few. I'll have to pause the video. So now that I've entertained the masses with some toys, let's keep going here. It says, example 1, a projectile is launched straight up into the air. It reaches a final height of 93 meters. What's its initial velocity? Use energy to solve this. We could solve this using kinematics. We could say A equals negative 9.8, V final equals 0, but I think we can also say, you know what? Come on, plus sign. We could then say, are any of these 0? Is our initial amount of kinetic energy, our initial speed, 0? Nope. Is our initial height 0? Is our final speed at the top for a split second 0? Is our final height 0? No. And we get this. A half mv initial squared equals mgh final. Mr. Dewick, I don't know how much the projectile weighs. Yeah. Why didn't I bother telling you? Megan. Turns out the mass cancels. And how would I get the VI by itself? What would I do with that 1/2? Times by 2. In fact, Megan, I think we get this. VI squared equals 2GH. You know what? Isn't that VF squared equals VI squared plus 2AD, but instead of 2AD, I have 2GH in disguise? I don't know if you remember when I showed you that equation, I said it was tricky to prove. It was way easier to prove when we got to energy. Well, there. It's way easier to prove when we get to energy. Oh, and how do I get rid of a squared? Then I'm going to cheat because I can and just go, you can scribble out the squared and put a square root on the other side. I think my initial velocity is going to be 2 times 9.8 times 93. It's going to be 2 times 9.8 times 93. 1,800 meters per second? That's like 4 times the speed. Oh, square root, Mr. Dewick. It's going, that's like 4 times the speed of sound. Wow, that's crazy fast. No. How about 42.7 meters per second? Is it still warm?
Oh, yeah.
So I bought these now. I don't know if they still have them, but the As Seen on TV store in Willowbrook Mall in Langley had it. Does Coquitlam Center have an As Seen on TV store? So they might have it there too. I bought these about 3 or 4 years ago. Then I put it on the physics listserv, and all the science teachers in the Lower Mainland probably cleaned them out, but they might have more. Because it was $20 cheaper for 5 compared to a science catalog. Gosh, they rip us off in science catalogs sometimes. Yeah, they have science teachers' catalogs with stuff, right? Well, you know, the little chrome spheres that I showed you, right? $80. That's a pricey one. It's such a cool demo that I spent the money, but some they would if I asked, probably, but it's usually easier and cheaper just to buy it myself. Then I can also say to other people, no, you can't use it. I did buy one of those things earlier, about 5 years ago, and the person who borrowed it tried to liquefy it by putting it into the microwave afterwards. And it popped, right? And they didn't buy me a new one. So I said, okay, I'll just use these myself. Isn't that a great example of an exothermic chemical reaction, though? Totally. Would fit well. In fact, Science 10 this year, bringing them out next week. I guess it means I got to boil them this weekend. Example 2, a 350 kilogram roller coaster car is traveling at 22 meters per second. If the car starts out at a height of 12 meters, how fast will it be going when it gets to the ground level? And here's the beauty. I don't care whether the roller coaster does that. I don't care whether the roller coaster does that. I don't even care if the roller coaster starts out this high, goes this high, and then does that. All I care about is the before and the after. Energy is a scalar. In fact, kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Plus heat. Oh, no, it says ignore friction. A half mv initial squared plus mgh initial equals a half mv final squared plus mgh final. Are any of these 0? I guess I could have asked that on the previous line. What's 0? Page? Ending up on the ground. Am I starting out at rest? Nope. Am I starting out on the ground? Nope. Am I coming to a stop? No. Okay, this is good. Oh, What else do you notice? Gabby, have you been on a roller coaster before? Did they step on a scale before, make you step on a scale before you went on the roller coaster? You know why? No, 2 words. Jaron, what? And even if we did include friction, now if we did include friction, since it doesn't have a mass in it, the masses technically don't cancel. Oh, do you think they grease the roller coasters to get friction as low as possible so that's within the acceptable safety zone? And even though technically the masses don't cancel, close enough. As long as we grease the roller coaster down, we're fine. There's a safety margin. We build it in. What are we trying to find? Oh, okay. Oh, what's in front of V final squared? You know what? Let's get really, really clever. Let's times by 2, times by 2, times by 2. Now, is that legal? Have I multiplied everything by 2? Then that is legal under equation solving. Now, why did I do that? Because Gabby, 2 times a half cancels there, yes? Oh, and 2 times a half cancels there. It doesn't cancel in the second term, but I get this. Vi squared plus 2ghi equals Vf squared. Again, call me silly. Isn't that Vf squared equals Vi squared plus 2ad in disguise? Paige, what am I trying to get by itself? How to get rid of a squared? Okay, I'm going to cheat and erase the squared and go chunk, chunk, chunk. You can scribble out your squared and put a big square root if you want to. It looks like it's going to be 22 squared plus 12 times 9.8. Not 12, Mr. Duick. 2 times 9.8 times 12. What a great question, Gabby. Ask your question. Let's see. Oh, wrong button. Gabby has said, hey, Mr. Duick, can't I just cancel out the 22 squared? Let's find out. Okay. Is that true? Is 9 plus 16 25? Is that true? Yeah? So you're saying, Mr. Duick, can't you just cancel out the squareds and wouldn't that still be true?
Okay.
Is it still true? Have I given you an easy way to prove that to yourself and convince you? By the way, whenever I ask a question like that, you can see, Gabby, my fallback is try it with dumb easy numbers that I can do in my head. And if it doesn't work with dumb easy numbers that I can do in my head, I better not be doing it with algebra, right? So then, if we do this correctly without canceling out the squared, what is the correct, what is V final? Sorry? 26.3, anybody else? 26.8 or 26.8? Oh, not meters per second squared, Mr. Duke, meters per second. How many of you enjoy going on roller coasters? Okay, we are going to be in May going to Playland as a field trip. How many of you enjoy standing in line waiting for the roller coaster? Okay, so here's your new game. The top hill, the first hill, what's your speed on leaving the hill? Close to 0. Close to 0. So if I'm standing in line, really, I can try figuring out how fast I am at the bottom of the first main hill by going 2 times 9.8. I don't want to do 9.8. What's a nice number close to 9.8 if I'm standing in line doing math in my head? I go 2 times 10 times my guesstimate of the height of the hill. I estimate 1 trestle and then multiply by the number of trestles that because they always build roller coasters with like that trestle scaffolding structure. And then I can usually try and crunch the numbers while I'm in line and make a best guess as to how fast I'm traveling at the bottom of the roller coaster. Feel free to enjoy amusement parks in a nerdy method. You really do that, Mr. Duick? Maybe. Yeah, I do. Pardon me? Disneyland, you get so bored, that would be good?
Yeah, because you're waiting in line all the time, so you get your
But it's the happiest place on earth, even in line. Have you been to Disneyland lately? Okay. They have improved the lineup process a fair bit because they've added like shade for starters, right? And on some of the rides they have little entertainment. So I went. Did you go on the new Star Wars? You didn't go on the. Oh. Anybody been to Disneyland in the past year and a half? Okay. If you haven't, if you do go again, I'm going spring break this year again. You got to go on the new Star Wars. They reopened it. In fact, I was there 2 summers ago, about a week after they reopened it, and there is 54 different combinations of that ride. Yeah.
Like the same one that they had 5 years ago?
No. 2 years ago. Just completely redone. The effects are way better. And then for that one, they've added, if you go on that, you'll find they've added entertainment along the way while you're in line. They're trying to do that too. They have, you can have a conversation with C-3PO and he does phrases back to you, sometimes accurate, sometimes not. There's a droid who's like the equivalent of the airport security TSA who's making all sorts of jokes because you can see he's scanning luggage, and you see the x-ray of the luggage, and there's like weapons inside or a person hidden inside, or else, and he makes some kind of a comment about what he sees. Right? Anyways, back to here. An 18-kilogram object is dropped from a height of 40 meters and strikes the ground with a speed of 25 meters per second. How much heat energy was produced during the fall? This looks like a job for conservation of energy. But this time, since they mentioned heat, I'll say, you know what? The energy doesn't balance. Whatever's missing must have gone into heat. Just like when I smashed those chrome spheres together. All right. Are any of these zero? Potential energy final, we hit the ground, that's zero. Oh, dropped means VI is zero? How would I get the heat by itself? Because that's what they're asking me to find. Now, this drives me crazy. There is a question on your test where I ask you to find the heat, and the number of kids that divide by kinetic energy drives me crazy. And I don't get it. Because it's supposed to be not an easy question, but I'm expecting most of my kids to get perfect on this question. Don't do that. You minus it. In fact, you're going to get In fact, Gabby, what we're really saying is this. You want to know how much heat is left over? Here's how much energy you started out with. Here's how much energy you had at the end. Whatever's missing must have gone into heat, heating up the air, heating up the ground. M, 18. 18 kilograms, about my little cannonball there. G, 9.8. H, 40, minus a half, 1825 squared. How many joules of heat was produced during the fall? Sorry? 1,430 joules? To 3 sig figs, right? I think it's 31 point something or something. Is that right? But 3 sig figs? No? Yeah. By the way, most common mistake, people miss the squared. Don't do that. By the way, this is the energy transformation that we're doing with our hydroelectric dams. Sort of. The water has potential energy at the top of the dam. We run it through big pipes downhill. The potential energy starts to become kinetic, but we bleed a lot of that kinetic off by getting the water to turn turbines, which then turns into electricity. The water comes out at the bottom far slower than it should because it's lost a lot of its kinetic energy. Hydroelectric power, once you've built the dams, it's a wonderfully clean, pollution-free way to generate power. The problem is when you build the dam, you damage an ecosystem. And so we built a bunch of dams in the 40s, 50s, and 60s, and 70s, not really having a good understanding of how that would damage the ecosystem. How's BC's salmon fishing industry doing right now? When I was 6 years old, 7 years old, I did a paper, a little report, you know, a 7-year-old report, so it was lots of pictures and stuff, on salmon fishing in BC, and I still remember at that time it was the second biggest industry in the province. I'd be stunned if it was top 10 now. I don't think it is. Right? But our power bill is pretty low. In hindsight, we didn't know, we thought, yeah, you know, the rivers will recover or the salmon will go elsewhere. We didn't realize how fragile nature is. It's both more tough and more fragile than we realize. Okay, shifting gears a little bit. Still warm?
Yeah.
Mm-hmm. Jason's over there. Oh, this is wonderful. This is great. Example 4. How much what? Work. Okay, now they're asking me to find work. Jaron, work is what times what? Read the question. Is there a force or a distance mentioned in this question? No. Okay. Work is also the area under a force versus distance graph. Is there a graph here? What was our third definition of work? The work energy theorem. What was it? Yeah, change in, you know what? It's change in energy, or in our case, it's going to be change in potential plus change in kinetic. Although I think, Jaron, I'm going to assume we're starting and staying on the ground. I think the change in potential is there. It's really change in kinetic. Work is going to be a half mv final squared minus a half mv initial squared. Because change in anything, Gabby, is final minus initial. Are you picking up why I kind of went on that rant for a while? Do the masses cancel this time? No, why not? Oh, there's no mass in the expression W, which makes sense. Is it harder to stop a bus or to stop a bike? The masses shouldn't cancel. It should make a difference. So I'm okay with that. 0.5. What's the mass? 1200. V final. Oh, what's my problem with V final? You know what? I'm going to get really clever. I'm going to go 50 divided by 3.6 right in my equation, all squared. That way I don't have to worry about rounding off or sig figs. Or I'll just do it right in the equation. Minus a half, 1200. 80 over 3.6. There, now it's meters per second squared. Wasn't that smart? It's also less writing. Where's the 3.6 come from? Going from kilometers per hour to meters per second. It's divided by 3.6. That one you got to kind of have up here. Or you can derive it. I think you're going to get, call me silly, a negative answer, aren't you? Try it. I'm doing some of the math in my head, and I'm definitely getting a smaller number minus a bigger number. I'm getting around negative 100,000. A little higher than that, I think. I'm doing the math, but instead of using 3.6, I'm dividing by 4, because that I can do in my head. And then I'm just kind of subtracting a bit to figure that I'm a little... No, I should be adding a bit because I'm dividing by too big a number. What do you get? Negative something, yes? Negative definitely? Negative what? Josh, what'd you get? Yeah, I know. Diana, what'd you get?
Negative 180,585.
Negative 1.8 what? So 1.81 times 10 to the what? Why negative? Pardon me? Okay, slowing down is the answer for last unit because we were talking about direction and acceleration. This unit, what does the negative tell you? You've lost energy. That's really what it's saying. You got less kinetic energy than before. It also tells you which way is the car traveling, forwards, which way is friction acting, in the opposite direction. It's bleeding off energy. Oh, what force does the work? I just told you. Friction. Where do you think the energy is transferred to? Kinetic energy's got to go somewhere. Where does it go? Jaron. Lots of heat. How much heat, Tyler? Enough that big trucks on long hills have an issue, right? They have to gear down. In fact, most of them will choose to gear down rather than use their brakes quite a bit. Or if they're not that good a driver, but think they're a good driver, they'll just put the clutch in and coast and go really, really, really fast. The problem is if anybody cuts them off when they're going really, really fast, there's an accident waiting to happen. Example 5. A 12.5 kilogram object is pushed across a level floor with mu 0.35 for a distance of 6.4 meters by an applied force of 58 newtons. You know what? Let's dulp. I got room at the bottom of the page here. There's the floor. There's the object. Nice, Mr. Duke. It almost looks professional. A says, how much work is done by the applied force? Jaron, force is what times what? Is there a force and a distance given in this question? Oh, so we can use your definition. Okay. The work, how about we call it W applied for work done by the applied force, is going to be F applied times distance. What's the applied force in this question? 58. What's the distance in this question? 6.4. How much work did let's say the applied force is a person pushing. How much energy did this person lose while they were pushing? 171 point, give it to me to the whole thing. 171 point what? 171.2, and then we'll round to 3 sig figs. Oh, 371. Sorry, couldn't hear you. How much work is done by friction? I think the work done by friction, B, is going to be force of friction times distance. Let's go to my drawing. What are the forces acting on this object? Get the obvious one, mg. Normal force, yoink. Applied, yoink. Friction. Friction is what times what? I don't know the normal force. Oh, but look. I know another force the same size as a normal force. What? This time, friction is mu mg times the distance. It's going to be 0.35 times 12.5 times 9.8 times 6.4. And I get 274.4, yeah? 274.4 or 274 joules of work. Why am I technically wrong here? Because I am. Opposite direction of motion. I'm losing that much energy. So even though this person is giving 371 joules of energy, not all of it is going into making this object slide and speed up. A lot of it is going into heating up the floor. What's the net work done on this object? There's two ways to do the net work, so draw a little line down the middle like that. The first way is to simply say the net work is going to be the work done by the applied force take away the work done by friction. It's going to be 371.2 take away 274.4. Now you could say, Mr. Dewick, you said that friction was negative. Okay, if you treat friction negative, it's actually the applied work plus friction. What I'm really saying is it's how much you started with, take away the value of friction. What is the net work? 106? 96.8. Joules. That's one way to do it. And that's probably how I would do it if I had done part A and part B as if they gave me this question. Now, if they just gave me part C and didn't walk me through part A and part B, the net work is also the net force times distance. Where the net force is going to be winner minus loser. Who's winning? Equals MA, but instead of writing MA, I would say, hey, that's my net force. What's the applied force? 58. What's friction? Mu times the normal force. I don't know the normal force. Oh, it's going to be mu mg. That's your net force. In fact, if I take that applied force of 58 minus friction, which was 0.35 times 12.5, try that again, times 12.5 times 9.8. That's my net force right there. If I multiply that by 6.4, holy smokes, what do I get exactly? 96.8. Which one's right? Whichever's less work. I guess the right-hand method is more universal. And since we just did a whole bunch of finding net force, just be careful, you're finding the net force, not the acceleration. We're used to always dividing by m to get the acceleration by itself. Don't do that, leave the m over there. Turn the page. Assuming the object started from rest, what will the final speed be of the object after 6.4 meters? What's this question asking me to find? VF. Speed or velocity? What do they ask for? And this is important. Speed or velocity? What do they ask for? Speed. If I'm doing a word problem and they ask for speed, my first thought is that's a scalar. I bet you they want me to use energies, not D equals VIT, not VF equals VI plus, not the kinematics vector equations. That's going to be handy towards the end of the year, like on your final exam. You have a word problem. Oh, speed. Try energies first. It'll probably be easier. Doesn't mean you can't get there with kinematics, but it usually means energy and get there a lot nicer. I'm going to say work equals the change in kinetic energy. Plus the change in potential, but look at my picture. It was staying on level ground, so the change in potential is 0. Work equals kinetic energy final minus kinetic energy initial. Are any of these 0? It says starts from rest. And here's what we're really saying then. Your final kinetic energy is equal to the net work on an object. Kinetic energy is a half mv final squared. And we just figured out what the net work was. 90, what was it? 96.8. Okay. How would I get V final by itself? What will I do with the 0.5? Times by 2 or divide by 0.5. What will I do with the m? Divide. What will I do with the squared? So, Jaron, if I hear you correctly, and holy smokes, I think I do, you're saying V final is going to be 2 times 96.8 divided by the mass, divided by the mass, divided by the mass. What was the mass? 12.5? Square rooted. Here's another way for us to find. Now, the other way, what do you get? First of all, crunch the numbers. That one is not wanting to go. You get 3.94 meters per second. The other way you could have done this then is you could have gone winner minus loser equals ma. You could have found the acceleration. You could have let vi be 0, d be 6.4, and I think you could have used vf squared equals vi squared plus 280, and that would have got you the same answer. Which one's better? They're both fine. Solve for A, winner minus loser, applied minus friction equals MA. That would get you there too. So we have a spring in a toy gun. Requires an average force of 1.2 newtons. I made these numbers up, by the way. They're not quite accurate. So when I pull this back, I'm exerting 1.2 newtons of force, and I'm pulling it back a distance. See it? In the numbers that I made up, I said I'm pulling it back 3 centimeters. Is there a force? Yeah. Is there a distance? Yeah. Have I done work on this toy gun? Yes. I've just given it some stored potential energy. Let's call it elastic energy, I guess, stored by a spring. I don't know. When I pull the trigger, an energy transformation occurs. All of the elastic stored potential becomes kinetic. Oh, that's a lie. All of it? Did you hear it fire? Okay, not all of it. Some goes into sound. Actually, a lot of it goes into friction. This is not a particularly efficient device. But supposing all of it did go into kinetic energy, how fast would the bullet leave the gun? Okay, kind of cool. A says, how much elastic potential? Work is force times distance, and work is the change in energy. You know how much I change the energy by? By whatever that force times distance is. Force, 1.2. Distance, ooh, why can't I use 3? 0.03. And I get 0.036 joules of energy. Not much. Although maybe there's not much mass, maybe I don't need much. All right. I'm pulling the trigger on Tyler here shortly. Supposing all of the elastic stored, all of the potential energy becomes kinetic, how fast will it leave? Now, really what we're saying is this. All of the initial potential turns into kinetic final. What we've really done, though, is we've used the law of conservation of energy. We said kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. But we said, you know what, Dorothy, it's not moving at the beginning, so it has no kinetic energy. Oh, and when I pull the trigger, all of the potential is now gone, so it's all kinetic. With me on that? All right. Oh, not MGH, Mr. Dewick. That's gravitational potential energy. 0.036 equals a half mv final squared. I think the speed that it leaves at after I pull the trigger is going to be 2 times 0.036 divided by the mass and then square root that. The mass is 10 grams. Why can't I use 10 kilograms? Okay, 10 grams. How many kilos? 0.1? 0.01. 0.1 is 100, right? Because 1,000 in a gram. So 0.01. What's my muzzle velocity if these numbers were accurate, which they're not? 2.68 meters per second. So that means if our numbers were correct and I stand about 2.68 meters away from Tyler, 1, 2-ish, how long would it take for the bullet to hit Tyler? 1 second. Oh, misfire. Did it take 1 second to get to Tyler? No, my numbers are way off. It took about 1/3 of a second if I was going to guesstimate, right? I was aiming high. It was John there then. Okay. We are kind of running out of time here, Mr. Dewick. I got a few more I want to do. I'm going to take a gamble. I'm going to try giving you some homework right now, and then I will pick this up on Monday when I see you folks next. So I'm going to say we can try number 1. This is what I'm eventually going to assign on Monday, but you can try seeing how many of these you can do right now. Number 2, number 3, 4 is good, 6 is good, skip 5, 7 is good. So skip 5 and skip 8 is where we're at right now.